and I'm going to give a kind of overview of various multi-scale aspects of materials modeling. I should say at the start, I mean, this is my own views, that this is a huge topic, and so I'm going to try to summarize a lot of different work. Lots of it is not mine. I may therefore misrepresent people's work, and that I completely own those mistakes. But hopefully you will still get something useful out of this talk, and I'm going to talk about the links between models that are used for computational material science at different levels and the links between them. As a starting point, I mean, I don't think I need to persuade anybody in the room at IPAM today that there are multi-scale aspects of materials modeling. So we know, in my own area of interest, I'm interested in crystalline materials particularly. So we know, of course, that crystalline materials have regular repeating structures. And if that was the end of the story, then everything would be nice and simple. But of course, it's not really that simple. We know that there are a huge range of defects that play roles in the mechanics and properties of these materials. So we've got point defects, right, like vacancies and interstitials. We've got line defects, dislocations, and then we've got 2D defects like grain boundaries, and you could even say we have 3D defects as well, like precipitates and microfractures, this kind of thing. So all of these different things occur at different scales. And in this particular, the way that I'm casting them here, they have different kind of dimensionality and therefore different sizes. And so inevitably, we can't simulate them all using the same methodology because either the spatial resolution needs to be higher than we can achieve, or the time resolution needs to be higher than we can achieve with with the most accurate models. So that means that we need to connect different models of these different phenomena in order to study the properties of materials and to make predictions about those materials, right? So the important aspect of computational material science, as far as I can tell, is that you can really actually create a new material in your computer and see how it might behave without having to do very expensive experiments. So if you're searching in a very large search space, this is where we have an advantage with computational methods. Okay, so then what are the modeling approaches that you might come across for materials modeling? So I guess I'm going to talk about kind of 4 levels of this, but there's lots of there's other things you could put on the diagram I've drawn here. So at the bottom, as you've already heard about this earlier this week, you've got density functional theory. So really doing quantum mechanics, or as close to quantum mechanics as we can get at the lowest length scales and with the highest accuracy. And then at the scale above this, we have molecular dynamics, which you've also heard about in Tim and Danny's talks. And then at higher levels, we've got things like dislocation dynamics theories and finite element methodologies for studying PDE models. And so those are kind of a different type of model. And each of these modeling strategies has different length scales that we can really computationally achieve, and also timescales, right? So this is the classic multi-scale modeling diagram that anybody who does talks in this area draws, right? Some kind of, I have to, if I want to get to longer length timescales, then I need to also scale my length scales up, because I just can't afford the number of degrees of freedom that would be required to do things down at this accuracy. And I guess the other way that you can divide this diagram is really that there's 2 distinct flavors of models here in terms of the phenomenology of what we're actually describing. So at the bottom left, we've got models that really have a proper description of the nuclei in a material. So the atomic nuclei in density functional theory, or the proxy for the atomic nuclei in molecular dynamics. And at these higher length scales, we have to resort to PDE models where we've forgotten about nuclei and we're describing things through fields, deformations, displacement fields, this kind of thing, continuum field theories. And so obviously we can ask, well, what connections can we make between these different levels of theory? And so I'm going to talk about 3 in my talk today. So some of which will overlap a little bit with stuff you've heard in other talks based on what I've seen on YouTube. So I'm going to talk a little bit about recent developments in machine learned interatomic potentials. And you will be able to hear much more about that, I think, during the long program. So those are basically the way to get accurate potentials for molecular dynamics starting from quantum mechanical calculations. I'm going to talk about atomistic to continuum methods. So how can we use information from continuum mechanics to inform calculations at the atomistic scale and vice versa? And so I'll talk about that in the second part of the talk. And then in the final part of the talk, I'll talk about sort of continuum to continuum methodologies. So how do we take a model that is kind of a PDE model at one scale and relate it to a PDE model at a different scale, maybe where I want to have some fluctuation in some material law, and I want to understand how can I effectively make predictions more simply using a simpler model. And that's the process of homogenization that we'll talk about at the end of the talk. Okay, so the starting point, I'm going to basically go up scales in a kind of natural way. So I'm going to start by talking about this link between machine learn, or link between DFT and molecular dynamics that we can make and has been a major development in the field in the last sort of 10 years. And that's through the idea of machine learned interatomic potentials. So as I've said, this is not my work. I mean, Warwick is a place where there are lots of people doing this work, but it's not something I'm familiar with, except in that it's in the air, let's say, at Warwick. If there are questions you want to ask, there are people who will be coming to IPAM who are probably a lot better qualified to answer some of those than I am, but I will try to give you my view of what is going on in this area. Okay, so the starting point that I want to I'm going to set some notations so that we can talk about it. So I guess in these atomistic theories, these discrete theories, fundamentally the degrees of freedom we care about are the positions of the atomic nuclei. And also in DFT, we want an electron density that's parameterized in some way. But fundamentally, in terms of making predictions, these are the degrees of freedom that we would move around if we're doing some kind of dynamical simulation. And then related to those degrees of freedom, we want to make predictions about the energy of the degrees of freedom and the forces that are acting on those degrees of freedom. And typically we're talking about ground state energies. I mean, there will be applications where we don't just want that, but so ground state quantum mechanical energies, which we would then differentiate, if we can do so, to find the forces that are acting on the nuclei. And therefore we can find, so for example, if we knew how to compute those forces the whole time, then we can integrate Hamiltonian dynamics to actually study how the system evolves in time. Or we can also solve equilibrium problems. So by asking that the forces on all the atoms be zero, and then study what equilibria look like. So potentially looking at local minimizers and saddle points in the energy surface, which would correspond to these forces being zero. Okay, and I think as probably has been discussed, the point is that DFT energies are very expensive to evaluate per atomic nuclei that you include, because you're fundamentally solving a nonlinear eigenvalue problem that needs to be solved iteratively, as far as I understand DFT. And so that obviously costs a lot computationally, and so that makes it very challenging to do dynamics on using DFT directly for more than a few atomic nuclei. On the other hand, as has been talked about, I think in Tim Gurman's talk, we have there's plenty of models for easy to evaluate energies, potential energies that describe interactions between nuclei of different species and that are used for molecular dynamics. And those are empirical and fitted to experimental data, to DFT data, and inevitably, because they tend to traditionally have simpler functional forms, they're much cheaper to evaluate, But on the other hand, the accuracy can vary. So you try to fit some number of parameters, and you can fit those very well, but then the other ones that you would like to also predict maybe not so accurate. And so in the last 10 or so years, the idea has been to try to use the techniques of machine learning to get more uniformly accurate predictions of lots of the observables that we care about, like elastic coefficients and so forth. So in terms of the general methodology for fitting one of these machine learning interatomic potentials, the way it works is as follows. So basically, the idea is, generally speaking, to use lots of quantum mechanical calculations or DFT calculations, which are viewed as the most accurate energies that we can get. And what we do is we compile a series of structures, so a series of representative sets of atomic positions and corresponding energies and forces that come from DFT for those things. And so we make a database of those things. So sample the configuration space of the material that we're interested in, and match up configurations with energies and forces. And here there's expert knowledge required, typically, because you need to know something about the properties of your material that you would like to be convinced that your interatomic potential is going to accurately replicate. So, for example, you might want to, if you're talking about some kind of crystalline material, you might want to include lots of strained crystal states to work out what the elasticity is and include that in your database. You might want to look at stacking faults. You might want to look at dislocation configurations. You might want to add vacancies in there. And so by including those in your database, you're going to use machine learning to actually fit a potential that already knows about lots of the material science that goes into this material. So once you have compiled such a database, and of course, this is not a linear process as I'm presenting it, but it's a kind of non-linear process, you need some way to actually represent the relationship, or you'll need a way to parameterize the atomic positions and you want to create a mapping between the atomic positions and the energies and forces that you have. And so the thing that has been developed over the last few years is the idea of, or one of the many ways that this has been developed over the last few years, is to encode information in descriptors. So a descriptor is just a set of variables that you can use to kind of compress this very complicated configuration of interatomic positions in an efficient way. And so typically how these work is they encode something about the environment around each of the atoms in the structure. And so in a way, what you're doing is you're taking that environment and somehow reducing it down to a few degrees of freedom, or as few degrees of freedom as you can get away with, that accurately represent the interatomic environment, and often in a way that's not, I guess, completely intuitive and clear, but I'll talk a little bit about what the reasons behind the way that lots of these descriptors work is in a minute. Okay, so we've got a database and we've got a way to compress the information that we've had to design to describe the interatomic positions. Right, I should also point out that, I mean, of course, these structures, when we have each atomic position has 3 degrees of freedom associated to it in 3D space. And so by the time you get to 100 or 1,000 atoms, which is not even that many, you've got thousands of degrees of freedom, right? And so that is a complicated set of, in a very high dimensional vector space to reduce down. And so part of the kind of cleverness of these machine learning interatomic potentials is to reduce that information in an efficient way. Okay, then once we've got a way of parameterizing and describing the environment that we have, we need to find a way to actually parameterize the energy using the variables that we've chosen. And so that might be through some kind of neural network, might be through some kind of polynomial method, representation method. It could be some blend of different approaches. There's lots of choices here. So that's kind of another user-informed thing that you can do. And once we've parameterized a class of functions, we also then need to do regression and fit. So given the output of the DFT calculations and the positions we have, we turn the positions into the descriptor, and then we try to do regression on the mapping between the descriptors and the energy and forces that we want out. So I guess the general view is that the way in which you encode this information, and so kind of the parts of 2 and 3 here are the places where you can really make efficiency gains or losses depending on how you do this. So regression, I mean, there's lots of regression methods are well known, and I guess this is where, you know, the existing material science knowledge goes in. But these are the 2 parts that really require some new knowledge or new expertise. And so the idea, maybe at a high level, behind a lot of these descriptors, particularly ones like gap, is that you want to essentially remove symmetries from the description of your material. So, for example, you know that, we know in classical physics that we have with Galilean transformations that are physics is invariant with respect to, right? So if I translate something in space and if I rotate it, then essentially up to translation and rotation, I will get the same results. And the idea is that somehow if we want to compress information efficiently, we want to remove those symmetries from whatever our descriptor is, because by building those symmetries into the descriptor, we make the extrapolation properties of our descriptors much more efficient. Right? So just from a few interatomic positions, we know that if we build the descriptors with these symmetries, then any symmetrically equivalent version of that configuration will also be encoded in exactly the same way. And so we automatically get frame indifference properties for free. The other symmetry that's important in material science is when I swap atoms in a species, then I want to include that permutation invariance as well in my descriptor. And that's typically a little bit more challenging to include. But if you can include that as well, then you are well on your way to reducing the information in a significant way. And so I won't talk in detail about how you go about doing that, but like I say, the SOAP descriptor that's used, for example, is one where these symmetries are effectively integrated out and allows us to reduce information by integrating out translation and rotation invariance. But I guess, the take-home message here is that efficient representations of the interatomic nuclei integrate out symmetries, and that's sort of the key to their success, I think, in part. Like I say, though, I mean, there are many, and it has been said, I think, in earlier talks, there are many such approaches. So I'm taking a lot of my diagrams here from a very nice review paper that came out that I will reference in a second, where they kind of give a family tree of different approaches. And I encourage you, if you're interested in this, to read that review paper, because it's very good and presents things very nicely. And so this family tree shows you kind of the different approaches that exist and how they differ and how they're similar in many cases. So we have, say, things like ACE and SNAP up here, SOAP, and lots of different other variations on machine learning approaches that are based on different kinds of coordinates and reductions of the information. So I guess maybe to wrap up this section of my talk, I guess I've tried to give some open questions that I think are relevant in each of the areas that I'm going to talk about. So in this area, I think, this is maybe a question that doesn't have a definitive answer, but there's a question about which architectures or descriptors are the most efficient in this space. And that particularly includes the idea of asking about which ones are complete in a mathematical sense, in the sense that if I Yeah. So typically you have some description in terms of these descriptors, but you're going to have to truncate your approximation of the information at some point, because you want to reduce the number of degrees of freedom to actually fit something in a fairly efficient way. But theoretically, we can continue increasing the complexity of our descriptors. And then there's a question about which of the choices of descriptors that exist or have been proposed are actually complete with respect to the information that we want. And is there a way in which we can quantify the rapidity with which we actually represent the information that's relevant for a particular molecular system, or a general molecular system as well? So that's, I think, an open problem that probably needs more research from the mathematical side. Then there's a bigger question that's perhaps of more pressing practical importance, which is that we now have, I think, very good methods for generally sort of one species or maybe two species. But if you really want a very complicated multi-component machine-learned interatomic potential, there's a big question about how you efficiently search through a very large combinatorial space. So in superalloys, where you have maybe, I don't know, on the order of 10 or more different components that you would like to include, if you want to design an interatomic potential that actually captures all of that, then I need to have interactions between, lots and lots of different components at the same time. And whilst it's now efficient to fit interatomic potentials that are accurate for a few of those components, doing it for all 10 at the same time, which might be necessary to properly describe the material science, is a major challenge. And so I think this is a direction that's going to be of interest in the future. As I said, if you want to learn more about this stuff, I encourage you to read this paper in Chemical Reviews that's been written by various people that are kind of leaders in this area, and presents a very nice overview of different approaches. As I said, the diagrams I've just used in the last couple of slides are taken from there. So it's nice and clearly written. So that's a good place to start if you're interested in this. I guess, given that I'm at the end of this first section, are there any questions that people want to ask at this point?
Said that the training sets are simple and only require expert knowledge of like constructing it, but I wonder if we also have to change the training set if we move from classical potentials to more machine learning potentials. Because I think we have so much more flexibility in the descriptors and in the parameterization.
Yeah, so like I said, I think I said at the time, let me go back to here. There's a bit more of a nonlinear process than I maybe presented it as here, right? Which is that I might also need to explore this space more, exactly as you're suggesting, I think. So I might have some idea structures that I want to put into my database, but then I might try and fit it, and then I might try and simulate with that potential and check whether or not I've actually got an accurate fit. And then I might find that indeed I need quite a lot more data than I started with. So yeah, there's a complicated nonlinear process in this thing, which is where I need to go sometimes backwards and forwards. I need to adjust the parameters that are involved. I might need to adjust the complexity of the descriptor that I'm using and things like this. Yeah.
But it could also be more complex, right? So if I have a lot of structures with the same crystal structure, that might weight my potential in a specific direction. Right? So let's say I train a lot on BCC, then maybe I'm not so good on the SCC, and to weight this all for I feel it was easy when we had like a couple of parameters for the classical potentials, but with these more complex potentials, it's much harder to see how do I build a good database that is representable, or like that really covers the whole space, and there's not like drastically weighted to like favoring specific crystal structures or specific events.
Yeah, no, absolutely, I would agree with that. I mean, there's still art in this, in exactly how you weight things, and yeah, it's not a completely straightforward process. This, yeah.
Other questions?
I had a question about the last question on your last slide, the one about element types. Yeah, so I'm just curious what you think is currently a very good way to handle different species. Like you can, with the descriptors, distinguish between types, and then let the model learn those differences, or let the maybe have a different model or set of parameters for each element type. I'm just curious what you think is a good way.
Yeah, I mean, so like I say, I'm not an expert in this, so I don't think I really have a good answer for this. I guess, yeah, you want to ask some of the people who are experts in this who'll be coming in workshops 1 and 2, because, yeah, I don't have an idea at the moment. I mean, I know that in principle, the idea that people use, at least that is being used here in Warwick, is that you often fit again, this is where the art comes in, right? It depends a little bit on the material science of your material and what you want the potential to capture. If you want to capture the 2 species individually, then you need to basically fit 2 potentials that describes those individual species, and then you should fit the interaction between those 2 species, for example. And there's a complicated balancing act there to decide exactly how to do that. But yeah, in terms of going beyond 2 species, I think it's still very hard to do this. And I think even for 2 species, it can be a major challenge. So yeah, I think there's a lot to be done.
I think one of the predominant ways they do this, especially not necessarily for potentials, but predicting bulk material properties, is instead of using these classical descriptors, do the combination of the descriptor and the learning model and use the graph structure to actually represent your material. And in that way, you can kind of define the dimensionality to some arbitrary length. And you don't necessarily have to worry about the combinatorial problem.
Yeah.
Further questions? If that's not the case, I guess we can continue.
Okay. So yeah, that was phase 1. So now I'm going to talk about the connection between kind of atomistic and continuum models. And yeah, so this is a little bit of a challenge because, right, we've got models that have kind of 2 fundamentally different phenomenologies of how they're set up, right? So at the atomistic scale, we have nuclei positions, and we need to somehow turn that into continuum fields or vice versa. So in elasticity theory, we typically have displacement fields or deformation maps to describe the positions of points, material points, but those are not the same thing as atoms and vice versa. And so mapping those one to the other is a challenge, but there are various ways to approach this. So to just set some terminology, when we're thinking about one way to try to map atomistic approaches to modeling onto continuum approaches is to sort of, at the basic level, just think about some reference, particularly in crystalline materials, think about reference structure, like the crystal structure that I assume is the ground state structure for that material. And then think about how those the atoms in that structure are deformed under some, say, elastic strain. So I might take points in the reference atomistic structure and move them to new positions in 3D space. And this is what I will call a deformation map for atoms. The next thing that we typically have in most molecular models, at least for MB type potentials, is we have a local site energy, right? So we have some way to turn the environment of this atom into an energy that really depends on some local environment that doesn't stretch too far. So typically in molecular dynamics, you enforce this with some kind of cutoff radius on empirical potentials, but yeah, there's also ways that for, say, insulators, you can actually show that this that there's some kind of locality property even from, say, a type binding model. So this is something that is established mathematically for some materials, and it's something that we typically assume in most models. So then I'm going to basically define a molecular dynamics type energy as a sum over site energies. So suppose I sum over the energy. So the site energy is VL. So the site L corresponds to this red atom here. And the site energy is describing the interaction between that atom and its local environment. And so if I want to get the total energy of the crystal, then I should sum up the site energies over all the positions in the crystal. And okay, I might need to normalize this to make sure that I actually get, I don't double count. But formally, this is how I can represent the total potential energy in my material based on an arbitrary motion of my atoms under the map Y. And frame indifference tells us that we should have a dependence of this energy only on the relative positions, the displacements between the atoms in the structure. And so as a very simple example of how you might do this with just a pair potential, right, I can define a site energy by just summing over the pair potential evaluated over displacements between atoms in the local interaction radius of the point that I'm interested in. Okay, and this is, at least perhaps not how it's implemented, but it's certainly the philosophy behind how you compute energies in molecular dynamics. Okay, so I'm going to talk about kind of molecular statics now. So we'll come to dynamics a little bit later on, but I'm going to talk about molecular statics because typically when we're trying to identify mechanisms for what's going on in atomistic models, we're interested in local minimizers and saddle points. So local minimizers, because those are the kind of metastable states in our energy landscape, and saddle points, because those are typically the saddle points that you must pass close to in order to transition between different locally stable states in the energy landscape. And so, yeah, we're interested in, so if I've got an energy, E, then I'm interested in the deformations, the motions of the atoms Y bar that solve the first derivative of the energy being zero. So that's effectively the same as the force balance, the forces on all of the atoms being zero. Right. So I'm looking for critical points of the energy, whether they be local minimizers or saddle points. But there's an issue here, which is, of course, that if the reference problem in a sense for crystals, if I'm really in the bulk, is basically that one of these deformations really occurring on the infinite lattice, right? So if I'm interested in states that look like this one, so like the vacancy that I've represented here on the right, the reference problem is really this vacancy embedded in an infinite crystal. And so the energy is defined on an infinite dimensional space of deformation maps. And moreover, this energy is, of course, non-convex because I'm looking for local minimizers and saddle points. And we know there are lots and lots of local minimizers. For example, it's easy to see that I can, if this state is a local minimizer, then just by moving an atom in to this vacancy and shifting the vacancy over by one, I'm going to get another local minimizer. And so there's a whole family of local minimizers that are related by translation invariance in this case. So the reference problem is non-convex and defined on an infinite dimensional space. So that basically makes it very challenging to solve. But I guess we know in some sense where to look for the solution to this problem, which is that we know that the displacements near to defects very often decay rapidly away from the defects. And we know that because kind of the continuum elasticity theory tells us that this should be the case. And we use continuum elasticity theory to actually predict as a guess, initial guess, to search for these defects in the first place. So, one approach is to try to fix the far-field atoms according to some prediction that comes from continuum elasticity theory, and allow the atoms close to the defect to vary so that we can locally optimize and then find local minimizers or saddle points close to that point, right? And then, so I've said that we can use elasticity theory, but there's a question which is essentially how can we do this efficiently or as efficiently as possible in order to make sure that our algorithm converges as quickly as possible, or that we can do this efficiently, maybe in parallel for different areas in the simulation. If I want to check what's going on in a very large atomistic simulation, I might want to know what's the local minimizer that's occurring close to some defect, just to understand a little bit what the mechanisms might be happening there. And so I'm going to talk about boundary conditions and how we can approach this problem. And so, as I've alluded to, one thing that we know from experiments and experience is that the atomic displacements away from these discrete defects decay very quickly back to the lattice, right? So this is a TEM picture of a dislocation. And if you cover up the dislocation in the middle of that picture, it's very hard to tell that the dislocation is there. So if you can see the dislocation is there because you've got darker and lighter region in the center of the image, which is where the atoms are variously compressed and expanded on above and below the dislocation. But if you cover that up, you really can't tell that the dislocation is there, and that's because the interatomic positions decay fairly rapidly back to where they want to be in the lattice, in the far field. And they do this in a pretty smooth way, all things considered. Like, there's no obvious, non-smoothness in this field. And so we know that one way to get predictions is to use continuum linear elasticity theory. So this is something that was developed really in the sort of 60s onwards, thinking about defects by people 50s, 60s and onwards, by people like Eshelby and other people that worked around thinking about dislocations and precipitates and inclusions in elastic materials and how the material responds and what the decay of the fields that are predicted by this are. And even though the material is non-linear, we can still use linear elasticity because close to the lattice, things behave nice and approximately like linear elasticity. And so we can use that insight to inform our approaches to modeling and computation. So I guess in practice, it's very common to use periodic boundary conditions for lots of these problems, but there is an issue with doing that sometimes, which is that the periodic boundary conditions that you may be able to afford for your simulation may actually mean that the defect densities are very high and much higher than you would actually see in a real material. And if the elastic fields start kind of self-interfering with periodic boundary conditions, then we can sometimes, there's certainly uncertainty there about the validity of some of the predictions we make. So there are various approaches that have been proposed to handle not just periodic boundary conditions, which are things like using coupling methods. So this is where you take normally two different theories and link them together. So one such approach is like a QMMM approach, where I'm coupling DFT in a core to a molecular model, QM, quantum mechanics, molecular mechanics. So I'm coupling those two models there. There's also the quasi-continuum method, which couples molecular dynamics to some elasticity theory that's simulated using finite elements outside one core region. And there's also connections in this kind of area to coarse-grained molecular dynamics. So here in coarse-grained molecular dynamics, typically you're trying to push what you can afford with your given computational resources by maybe lumping atoms together in regions that are not so interesting for what you're trying to simulate. So I'll talk a little bit more about that later on. But I guess the proper coupling methods straight out of the box are these QMM and QC methodologies. Another approach that you can take is to use kind of flexible boundary conditions approaches, which are where we, people like Dallas Trinkle and his co-workers use this kind of methodology where you use lattice Green's functions to kind of predict the far field. So you use linear lattice elasticity to predict what's going on in the far field, and you kind of enrich the boundary conditions by allowing degrees of freedom that you can incorporate using that. To approximate far field strains. And that's kind of connected to some of these other approaches. It's just a different way of phrasing the same kind of idea. So I have some PDE theory that I apply in the blue region, or some approximate theory that I can solve nicely in the blue region, and I have something where I really keep the atomistic detail in the red region. I want to couple the two together somehow. So what are the challenges in this with these methodologies? So one of the challenges is that if you sort of naively mash two of these models together, you can end up with incompatibilities at the interface between these different regions, and that leads to ghost forces that can mess up what's going on in the center of your simulation, and mean that they don't converge to the thing that you want them to converge to, or at least they converge much more slowly than you would like them to. So there needs to be some sophistication in the way that you actually couple the two models across this interface. And I guess the other thing is, as I've said, this is really focusing on molecular statics. So there's also a question about how you actually do dynamics, because typically coupling two models together and then simulating them dynamically is going to mean not just that there's errors in the forces, but there might also be reflection effects, right? So if I have a region where I have one model and a region where I have another model, and I propagate some wave through the system, then I might get reflection off this boundary back into the center, which will then cause problems in terms of, say, the thermal transport in my material, which would then mean that the physics is going to be wrong. And so, yeah, there's still various challenges, I think, to be addressed here. The ghost forces have, lots of the work that's been done by Mitch Luskin, Christoph Ortner, and the people they've worked with in this area has addressed lots of different ways to deal with the ghost force problem. But I think the dynamics problem is still largely, unsolved, let's say. So in terms of some references for these kind of methods in the mathematical literature, I should say, there's lots and lots of these things, but there's a review paper by Mitch Luskin and Christoph in Acta Numerica that might be a good place to start. And there's a paper by Virginie, who's in the audience, and Christoph and Alex Shapeev that talks about kind of these different methodologies side by side that might be of interest. And there's a whole stream of other work that you can access by looking on from there. So I was going to also talk a little bit about coarse graining and talk a little bit about the challenges that come from that. And so coarse graining, I think, actually, as far as I understand, is used a little bit more in biomolecular simulation than it is in materials simulation, like crystalline material simulation. But let's talk about how it works anyway. So typically in lots of simulations that what we want to do, right, if we're focused on a particular defect, we have some region of interest that we care about much more than the entire bulk crystal, right? And so we might want to devise a model that really simulates what goes on in this region accurately and sort of treats everything outside of this region as something that, information that we want to somehow reduce, but we know that there are properties that of the interaction between this region of interest and the bulk crystal that we need to still capture. And so one way to kind of reduce the degrees of freedom in your model, but capture what you're interested in, but reduce the computational cost, is to devise some kind of coarse-grained model. And so one way to do this is just to sort of lump atoms together outside of a region into what are sometimes called beads, and think about a model which maybe represents these atoms exactly using a potential that we already have, and represent the interaction with these beads through some other fitted interaction potential. And so if I reduce variables in this way, so if I really lump things together into beads, then I can view that as kind of the word is escaping me, but as a coarse-grained degree of freedom, or sometimes called reaction coordinates, so a set of reaction coordinates that kind of allow me to reduce the number of degrees of freedom in my model. And we know various methodologies for trying to fit free energies for those degrees of freedom. So at some temperature, what is the effective potential that describes the interaction between this red bead and the blue beads, and this red bead and the other red beads outside. And so there are lots of methodologies that are well established to sample free energies. But I guess one thing that is a potential issue here is that while the free energy is a significant part of the story, it doesn't seem to be the full story. So in the sense that some of the dynamical properties of this system may not be accurately captured by the free energy alone. So one way to see this is to think about the reduction from these three atoms down to this one red atom. So this effective bead. So imagine that this red bead is the center of mass of these three atoms. So I know that like if I just fix the center of mass of this red bead, so the center of mass of the system, there are still further degrees of freedom that describe how the atoms, the gray atoms, are placed relative to that center of mass within the bead. And I can store energy in those degrees of freedom, and I can, that energy will fluctuate if I'm doing a dynamical simulation. And while on average, I will get the free energy out, the nature of those fluctuations will change how this red bead reacts in a dynamical way. So the fluctuations will store energy, and they will have a particular character that will affect exactly how this red bead fluctuates itself. So it's not just that the mean may be correct, but the fluctuations on top may have character that we are not predicting with the free energy alone. And so that may alter the timescales that we predict of various phenomena. And if we're interested in diffusion properties, for example, then that could be an issue because we may be significantly out in the prediction of diffusive timescales, for example. And so typically this is addressed by sort of realizing that there's an error in the timescales and rescaling things appropriately. But there's a question about whether we can do better and try to predict this straight out of the box in some sense. And so I think there's an open problem there, which is to try to find some kind of robust framework to actually fit, maybe with machine learning techniques, free energies and compatible thermostats that allow us to effectively devise coarse-grained models that we can then use to kind of reduce models and make better use of our computational resources. In terms of references here, so if you're interested in a reference, that's a good starting point to learn about effective potentials and free energies, then I can recommend this book by Tony Lelièvre, Matthias Rousset, and Gabriel Schultz. That's called Free Energy Computation as a Mathematical Perspective. But there are many other good references in this area as well. I mean, that's just my preference for a good starting point. And I think that, that takes me to the, that's no good. That takes me to the end of the second part of my talk. So I guess, are there any other questions at this point?
Yes.
Yeah. So I guess my question is somewhat related to coupling part of DFT coupled with MD.
Maybe you speak up and it's easier.
Oh, sorry. Yeah. So my question.
Is it okay? I can hear.
Yeah, you can. Yeah. So in one of the slides, you're talking about the coupling of DFT with MD, right?
Yep.
So how does that work? I mean, can you give me a brief? Because thing is in DFT we have electron densities and that kind of stuff. So the if I want to look at the interface between the DFT part of my system and the MD, that looks like a hard thing to deal with, right?
I think it is. Again, I'm not an expert in this. I'm presenting other people's work here. So again, James Commode here in Warwick who will be coming along, is again as someone who has great expertise in doing these QMM methods. So I think, I mean, as far as I understand, at a very high level, and I might be misrepresenting things here, the point is that you need some local basis set for your DFT calculation, and then you need some molecular model that somehow closely represents or accurately matches with your DFT calculation. So I think it's a challenge. I know James has done simulations in silicon, but it's really in pure silicon. And what they did there was look at silicon at a crack tip interacting with maybe one, I think it was hydrogen, I'm not sure, interacting in the crack tip region. So there you really have just one species that you're coupling, and so it's maybe an easier problem. But if you have a more complex material, then yeah, I mean, this I think is a very challenging thing to do in general.
I would also have a question. Do you have any assumption why the coarse grain with beads is not so popular for a solid? And what are maybe the challenges there?
I think it's. I think it's because I think partly it's a less well-posed problem. So in the sense that in biomolecular simulation, typically you're interested in, say, one thing that you might be interested in is a polymer. And there you have isomer units, which are kind of already neatly packaged up for you as a potential kind of reduction of your system, because you know that they have a chemical character that is, that each isomer has its own chemical character, and putting them together somehow allows me to maybe reduce the system in that way. And I think in a crystalline system, I mean, you have much more freedom to choose your coarse-grained things. I mean, how many atoms do you put into your bead? Do you put in 20? Do you put in 30? Do you put in 2? I mean, that's I think the hard point, is a less well-posed problem to actually decide what the degrees of freedom should be. And yeah, I think, but that doesn't mean that it couldn't work. It's just that maybe we don't yet know how to make it work. So yeah.
Thank you.
Could I make a comment on that question? So I think the fundamental difference between solids and liquids from the point of view of coarse grain is that in a liquid, the particles, molecules, whatever they are, on some time scale are independent of each other. They can diffuse away from each other, they can rotate. In a solid, all of the constituent elements are stuck with each other forever, both in time and in space. There's no change, and so there's a lack of independence from the solid that I think makes it more difficult to coarse grain.
And I guess that's actually, in some sense, another way of interpreting what I'm saying here. The fact that the fluctuations may matter is telling you exactly that there's a lack of independence in the system, and you can't just do this as nicely. So yeah, I think thanks for the comment.
Yeah. So this coupling techniques, mostly from atomistics to continuum, are mostly based on statics, right? I mean, mostly those are statics. So there is no finite temperature or thermal noise effect that's going into the higher scale of the models. So are there, I'm not sure how much progress is there on that front. Like how to take thermal noise or thermal vibrations, which might be important in the atomistic regime for some defect analytics, to a hierarchical model. For example, say this.
Yeah, so I guess I toyed with the idea of including some slides to motivate why you care about these. These local minimizers and these saddle points. And the point is that at least for relatively low temperatures, and even I think the heuristic that I've heard people say, and again, I'm not a material scientist, I'm a mathematician that tries to do material science, is up to about a third of the melting point, low temperature type approaches are valid. And that means that you can do things like transition state theory to say, if I have a vacancy like it's shown in the picture here, and I want to ask how does it diffuse, then all I need to really study is the local minimizer near to that. So the character of the local minimizer at where the vacancy sits, and also the saddle point where this atom nearby is moving into this, or one of the nearest neighbor atoms is moving into the vacancy. And I can then use transition state theory to basically say, predict or give reasonable predictions of the rate at which this is happening, and therefore the diffusive timescale of these kind of things. So while the statics might seem like it's all just zero temperature, it's actually works, or you can extrapolate information that you can gain from these static simulations up to higher temperatures using kinetic Monte Carlo type techniques.
But there are situations where, especially for dislocations or extended defects, where anharmonic effects are important. So your 0K saddles might not be the free energy saddles in fine temperature. So.
No, absolutely. I'm not saying that this is the be all and end all. And that's why I'm saying that fluctuations should be taken into account, and ideally would be. We don't yet have the means to do so. I think that's a big open question to address, to extend the timescales of simulations accurately.
Any further questions? Otherwise, we can continue with the next session.
Yep. Okay. So the last section I'm going to talk about is the kind of PDE model to PDE model connection. And so often we refer to such results under the umbrella term homogenization. But so I thought I'd just talk a little bit about some basics of homogenization. You can actually illustrate quite nicely with ODEs. So I'm going to illustrate with periodic homogenization and stochastic homogenization in a simple way. So let's suppose that I have a periodic layered material, which is in a nice rod that I'm subjecting to a tensile stress like this. So this might not be a particularly realistic situation, but it illustrates the idea behind. So if I'm thinking about this in a linear elastic setting, and I'm really thinking about everything in 1D, then what I know is that the force balance is going to be, if there's no bulk loading, I'm just going to get the derivative of the stress in the material with respect to the x variable is 0, right? That's my force balance, the divergence of the stress. And in 1D, that's just the derivative of the stress being 0. And if I have a linear elastic law, then I know that the stress is given by some elastic coefficient times the strain, so du by dx. And here, what I'm going to assume is that this elastic coefficient is oscillating on a scale which is of order epsilon. And so in this layered material, I have two different materials which I'm sandwiching together to make up my rate of material. And so the periodicity is on the order of epsilon, whereas I have some L, which is the length, the original length of my rod that I'm stretching, which is much larger than epsilon. And so what I'm interested in, right, is something like the stress-strain response of this material. If I know what the stress-strain response of the individual materials, the black and the orange materials are in this picture. Okay, and like I said, I'm going to assume that I'm applying a tensile stress at either end of the material. So that will just be sigma, give me the boundary conditions, flux boundary conditions, saying that the normal stress at the ends is tau. And so now if I look at this linear elastic equation and I integrate it once, then I'm going to get that the stress sigma is going to be constant throughout the entire material, in this case, in this very simple model. And of course, because of the boundary conditions, that constant better be tau. And so then that means that in this equation here, I can replace sigma by tau. I can divide through by k, and then I get the following first order differential equation for u, which I can then integrate and use the boundary conditions to work out, given the strain, the stress applied tau, what the kind of response is delta. So that's the percentage change in the length. So the strain is delta, because I'm saying delta L is the actual length change here. So this is a fairly simple ODE situation, so you can really work these things out explicitly out. But the thing that you see is that the effective stress strain here, right, is that, so the change in the length, or the percentage change in the length delta, is the torr times this whole thing as a coefficient, which I'm going to call K. So this has some complicated form, but the point is that it looks like, so if I've got 1 over K here, and I'm averaging over the domain, so, and then dividing by the length, so that looks, and then taking the inverse of that whole thing, right? So 1 over K averaged over the domain, and then inverted, and that gives me K. So that's basically the harmonic mean of the Ks that are in the red and orange region, the black and orange regions here. And so the point is that while this is all linear, the response, the effective response, is a much more complicated average harmonic mean of the different elastic coefficients in this case. And so the point is that we can work this out in this nice simple case, but in general, we need to do some work to actually work out what the effective response is if we have a layered or more complicated periodic material. But yeah. So here, this is just saying that if I had a fixed elastic coefficient K1 in the orange region and a fixed elastic coefficient K2 in the black region, then the volume fractions alpha 1 and alpha 2 for these two regions, then this would basically give me the effective elastic coefficient. Okay, so in a random material, so now instead of a nice periodic structure, I can just take slices of a material that maybe is, so suppose it comes out of, I'm making a layered material, but there's some variability in the manufacturing process. So each of these layers has a different elastic coefficient, but I know that they come out with some distribution. Then I can also do some kind of homogenization result, so work out what the effective response is of this material. And the way you do it is this very similar to what I just showed you. So again, we're going to assume a linear elastic response. So the force balance is that the divergence of the stress is 0, and the stress is related to the strain by a linear relationship. And then in this case, I can do exactly the same analysis as I did last time. It's just that this time I have to average over something that is now a random field. The K in each of these different slabs is going to be randomly determined in general. And if I assume a property called ergodicity and my epsilon is sufficiently small relative to the length L, then this spatial average can be converted into an actual average of the random field. So I replace this spatial average that's inside here with a expectation, so the mean of 1 over K. So if K is random across here, a random elastic coefficient in each of the layers, then if I take the expectation of the inverse of those elastic coefficients, that gives me the inverse of the effective elastic coefficient in this case. Okay, so you can see that there's some nonlinear averaging process that goes on here, but nevertheless, there's some averaging process that allows us to tell, to say what we expect the properties of this random material to be, or what the properties of the periodic material should be. And so in a more general PDE setting, we might have a fully a linear elastic setting where I have an elastic coefficient tensor that might vary, and it might vary in a much more complicated way than this periodic layered structure. But I nevertheless have some PDE that I need to solve that looks something like this. And so now the theory of homogenization allows us to say rigorously that actually, if epsilon is small enough, we're going to get close to some problem where there's an effective elasticity tensor here, C bar, I've called it, that predicts basically how the strain response is going to occur. And in order to solve this, in most practical cases, we need to solve both a macroscopic PDE problem, so this PDE problem, but we also need to solve some kind of cell problem that tells us how to compute the C-bar. So in what we just looked at, the cell problem was actually very simple to solve because we're in 1D, so everything works out very nicely. But more generally, there's a whole separate cell problem that needs to be solved to actually determine C-bar. And that's a PDE problem that needs to be discretized in some way. So there's two PDE problems that need to be solved simultaneously. And whilst I presented this in this case for a linear setting, there are still ways that we can solve problems where we have a nonlinear elastic setting or a nonlinear response in other ways. So it doesn't have to be this elasticity PDE that we can do this to. We can do it to many different PDE problems. And in the random case, the cell problem becomes very complicated because we need to now sample sufficiently. The cell problem becomes possibly very large and difficult to sample. And so then there's questions about how we can do this efficiently, again, potentially using machine learning techniques. In terms of literature that you can look at to think about some of these things, in terms of the kind of two good references from the maths literature side, I can recommend Multiscale Methods by Pavliotis and Stewart. That talks about both averaging and homogenization, as it says in the title, but it actually talks about a lot of different techniques for reducing models, both ODE, stochastic differential equations, and PDE models. And if you're interested in the nonlinear setting, then one approach to doing this is to use something called gamma convergence. So that's used for variational problems, so problems that you can pose variationally and study via a particular kind of functional analytic methodology called gamma convergence. It doesn't work for every problem, and it doesn't always give you full details of everything, but it's a methodology that's very powerful and has been used on lots of different problems. So before finishing up, because I'm aware that my time is kind of coming to the end, I guess I wanted to just say that, I mean, there's a big, or the problem that's maybe closest to my heart in this area is kind of predictive plasticity. So we know the thing that I have spent much of my research career thinking about is really dislocations and line defects and how that relates to plasticity. And I think whilst we have models of plasticity at the continuum scale, there's actually still a kind of missing link between what we understand about crystal plasticity at the microscale and the macroscale. And it would be lovely in my research lifetime to see the connection between those things actually demonstrated. And there are partial results in this area in 2D cases, but actually for the fully 3D problem, I mean, this dislocation dynamic simulation, it is periodic. So if you look closely enough, you will see that there's the same block is tiled 8 times here, but nevertheless, it's still a complicated problem and requires some kind of homogenization that we don't yet fully understand. So there's major challenges in this area still. So I posted on Slack that there's a job advert in Warwick. So just before I wrap up, if you are interested in this kind of stuff, James Commode just told me earlier on that we have a permanent assistant professor position opening in Warwick, in the Warwick Centre for Predictive Modelling. So if you're interested in the kind of stuff that we're going to be talking about, I guess, in this IPAM program, then this might be of interest to you if you're at the right point in your career. And once I'm in LA, if you want to talk to me about that, I'm more than happy to do so. But now back to the conclusion. Multiscale methods continue to develop in computational material science, and we have various mature methodologies, but there's still lots of challenges, as I hope I've illustrated. And I think both theory development and numerical implementation, actually, of lots of the ideas that we already have important roles to play. And that's something that I'm looking forward to discussing with you all when I come out on Sunday. So there's various references there, and I'm happy to take any final questions. Thanks.